Okay, so in this video, we're going to cover integer representation. Keep in mind, this is not a generic method to represent all numbers because floating point numbers or real numbers with the decimal or fractional part are represented differently. So in a later section, we're going to show you how a real number or a floating point number is represented internally. But here we focus just on integer representation. So there's two things that we have to keep in mind. If the integer is unsigned, meaning no positive or negative sign, so by default it is a positive value, there's only one way to represent this number. And if the integer is signed, then we have three alternatives. We have sign magnitude, 2's complement, and 1's complement. Okay, the two most important ones for sign are the sign magnitude and 2's complement, but we'll see all three. All right, so let's take a look at the unsigned integer representation. So if the number is unsigned, then all that we have to do is just to convert the number to binary. Okay, so let's assume, here's an example. Let's assume that we're using 8 bits to represent the number 13. So this is how the number would be stored internally, okay, with 8-bit representation. Now, keep in mind that the rightmost bit is the least significant bit. So this has weight 2 to the 0, the next one 2 to the 1, the next one 2 square, the next position 2 to the 3rd, and then 2 to the 4th, and so on and so forth, like we've seen it before. Now, so I have a digit 1 in the 2 to the 3rd power, right? That would make an 8. I have a digit on 2 to the 2nd power, which is a 4. And I have a digit of 1 in 2 to the 0 power, which is a 1. So then when I add all three, I have the value 13. So this is the representation. Okay, this is the representation for the decimal number 13 using 8 bits. Now let's take a look at this example. I have an example here with 27. Let's convert the unsigned number 27 using 6 bits, assuming it is unsigned. So here are the 6 bits, 3, 4, 5, and 6. Now, in 6 bits, again, the rightmost digit or bit is 2 to the 0, next 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, 2 to the 5th. Okay, so this position is 32, because 2 to the 5th is 32. This is 16, 8, 4, 2, and 1. So I need to make 27 with these values. So I think I need a 1 here for 16. I think I need a 1 here for 8. So this is 16, this is 8. And that gives me 24. So I need 3 more, right? So I need a 1 here for 2. And I need a 1 here for 1. Okay, so if I add all of these values, I have 8 plus 2, 10, 26 plus 1, 27. Okay, so the rest I have zeros. So 27 is represented as 0, 1, 1, 0, 1, 1 in binary as an unsigned integer. That's all we have to do. Convert the number to binary. Okay, so this is very straightforward. All right, next, let's assume the number is signed. Okay, so when the number is signed, we have 3 different approaches. The first one that we're going to consider is called the sign magnitude. So the sign magnitude says that the leftmost significant bit, right, the one on the left, is going to be used to represent the sign. So if the number has to be stored in 8 bits, the leftmost one, the last one, is going to be used the sign. So the rest of the numerical value of the number has to be used or represented in the remaining 7 bits. Okay, we'll see here as an example. The procedure then becomes, if the number is positive, then the leftmost significant bit would be 0. And if the number is negative, the leftmost significant bit would be 1. And that's all that we have to do. We convert the number to binary, and the leftmost significant bit is adjusted accordingly for positive being a 0 or negative being a 1. So let's take a look at these two examples that I have. So first, let's do a positive 19 using sign magnitude, 6 bits. So here are the 6 bits, 1, 2, 3, 4, 5, and 6. Okay, but now this bit right here, okay, this is the most significant bit, as we call it, or the leftmost bit. This has to be the sign. So if the number is positive, I'm going to put a 0. If it was negative, I would put a 1 here. So the remaining value, the 19, has to be stored in these 5 locations. Okay? So let me show you again how to convert. Let's convert this. Again, this is 2 to the 0, 2 to the 1, 2 square, 2, 3, and 2, 4. I need to represent 19. So I would say 1 here for 16, 2 to the 4 is 16. And then I need 3 more, right? 1 here and 1 here. So this is 16, this is 2, and this is 1, and that's 19. So the middle values are 0. So positive 19 is represented as 0, 1, 0, 0, 1, 1 in sign magnitude, right? This is the sign bit. If the number is 30, for example, or minus 30, as you see here, the same thing applies. Let's use 6 bits, sign magnitude representation. So 1, 2, 3, 4, 5, and 6. Again, the leftmost bit, or the most significant bit, is used to represent the sign. Now, in this case, it's minus, so I have to put a 1 here. And now, in the remaining 5 bits, I have to write 30. And again, this is to write 2 to the 0, 2 to the 1, 2, 3, and 4. Let's hope I can represent 30 in 4 bits. Otherwise, I have to increase this to 7. So 2 to the 0, 1, 2, 3, and 4, right? So I don't know if I'm going to be able to do it, but I can try. If not, I would have to change this. So 1 here for 16, 1 here for 8, right? So this is 24. And 1 here for 4, 28. And 1 here for 2, 30, right? So there you go. So 16 plus 8 plus 4 plus 2. So this is 20, 30. So this is my 30. So this is the number 1, 1, 1, 1, 4 ones, right? And a 0. And this is the sign bit to represent minus 30. Let's convert the number into binary using 1 less bit than the total allowed, because the leftmost significant bit is used for the sum. So again, sign magnitude, the most significant bit, the leftmost, is 0 for positive, 1 for negative, as you see up there. All right, great. Now, the next approach is if we are using 2's complement. So sign magnitude is not very good, and 2's complement is the preferred method. You can read the details in the posted file. I'm just here concerned myself with the actual conversion. So in 2's complement, which is the preferred format that we are going to store numbers, we have a little 2 procedures for positive and negative numbers. If the number is positive, then the 2's complement of a positive number is just the binary. It's similar to the unsigned value. So we just convert the number to binary, and then we're done. If the number is negative, then we're going to convert it to binary first. We are going to flip all of the bits, and then we are going to add 1 to the final value. Okay, if the number is negative. If the number is positive, we just convert the decimal number to binary, and that is the end of it. So here's an example for minus 28. So we write minus 20, we write 28, positive 28 in binary. We flip all the bits, meaning all of the zeros become ones, as you can see here. Okay. So the 0 become a 1, the ones become zeros for all of them. And then afterwards, we add 1 to the flip bits. Your final answer is the number in 2's complement. So it's a 3-step process for the negative values. For the positive values, so here's an example. For the positive values, all I have to do, let's say that I'm using 6 bits again. 3, 4, 5, and 6. All I have to do is convert this number to binary, and I'm done. So 13 again, 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, and then this is 2 to the 5th, which I won't need. All right, so let's see, 13, I just need an 8, and 4, 12, and 1, 13. The rest is zeros, okay? So this is the number positive 13 in 2's complement, okay? That's all I have to do because the number was positive to begin with. So just write the number in binary. Now, if the number is negative, let's see the other example that I have. If the number is negative, right, then I have to do the 3 steps. First, you're going to write, and let's say that I'm using 6 bits. So I am going to, here are my 6 bits. The very first thing I'm going to do is I'm going to write the number 11 in binary in 6 bits. Okay. So again, 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3rd power, 4th and 5th. So 0, 1, 2, 3. So this is 8, 10, and 11. So here's my 11, right? Fill the rest with zeros. So this is the number 11 in binary. Now, because the number was negative, I have to flip all of the bits. So second step, flip. So 1, 2, 3, 4, 5, and 6. So the zeros become ones, the ones become zeros, 0 becomes 1, 1 becomes 0. So here's the flipped bit. Okay, bits. And then the last step is I'm going to add 1. So I'm going to say add 1 right here. All right. So I add 1, 0 plus 1, 1. So all of these are zeros, obviously. 0 plus 0, 0, 1, 0, 1, 1. So the answer that you get, this is the number minus 11, 1, 1, 0, 1, 0, 1 in 2's complement. And that's all that we have to do. Okay, so if the number is positive, just convert it to binary. If the number is negative, then do these 3 steps. Write the number in binary, flip all the bits, and then add 1. All right, this is the preferred form for computation internally, and this is the one that we are going to use. I'm going to show you how to do in the next video, numerical arithmetic in sign magnitude format in 2's complement, but 2's complement is preferred. The last method, which we are not very much interested in, but I'm going to show it to you anyway, it's the 1's complement. It's similar to 2's complement, but it's the same situation. Positive numbers are just converted to binary, and negative numbers, we do a 2-step. Negative numbers, we first write the number in binary, and then we flip all the bits, and then that's it. We stop. So obviously, there's one big problem here is that the ones complement scenario has two representations for 0. Here's a positive 0, and here's a negative 0, which is not very ideal. So that's why we don't use it. But I'm going to show you anyway. So again, if the number is positive, just convert it to binary. If the number is negative, then we do these two steps. So let's assume that I'm doing 6 bits again. But it could be 8, it could be 10, but I'm just doing 6 for simplicity. Again, this is 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, 2 to the 5. I need an 8. So you're going to write the positive number in binary here. So 8 is just, I have a 1 right here. Everything else is a 0. And then the second step is just flip all the bits. So I'm just going to flip. So 1, 2, 3, 4, 5, and 6. So the zeros become ones, the 1 becomes zeros, and then the zeros become ones. So the negative 8 in one's complement would be 1, 1, 0, 1, 1, 1 in one's complement. Okay, so these are the 3 methods for sign numbers, sign magnitude, 2's complement, and 1's complement.